Thanks a lot to the organizers and the leadership of OpenNebula for giving me the opportunity to talk to you all today. Just a little bit of my background. So I'm a failed molecular biophysicist by training. So my PhD was in protein structure prediction. And I've had a lot of great opportunities to work on the human genome, to work at the Broad Institute, and then over the last decade or so here at Harvard University. And so over 20 years, I've seen compute really kind of scale out from when I thought I was the bee's knees in Oxford University with a single silicon graphics underneath my desk that we used to call Speed, because it was the fastest machine that we had, to great scale for the human genome, and then later at Harvard, and the story I'll kind of get into. But it wasn't always like this. I started my career on a 380Z. This was a research machine, and it had some amazing properties. So as much as Ignacio said this isn't a sales pitch, just remember when you see these quotations that it can run very large programs. Text and graphics can be mixed on the screen at any time, right? So this was fundamental computing that was driving the research. And no more queuing, and virtually an unlimited computing budget as well, just to kind of go with that. So don't panic. And we had a network-attached storage device. We thought we were super clever, and we had a network. It's a network unlike you've ever seen, and you can read about how the 8 kilohertz clock drove this network. In any case, the compute has gone from big shared machines, where the machines were super expensive, you couldn't afford them and you had to share them, through to sort of departmental servers like VAX and of its ilk, and then the personal computer where, again, people began to own the computing again. Don Becker and crew realized that they could actually stitch a bunch of these PCs together, wrote an NE2000 network driver, and then started this whole clustering thing. And then they wouldn't fit under the desk anymore and had to go back into the data center. And so the rest is sort of history, but the challenge here is that at what level of sharing have we actually had across these computing platforms? So this was the first compute we built in the United Kingdom to annotate the human genome. I put this up because none of these technologies exist anymore, not a single one. But we did manage to annotate and inform the human genome, so the computing worked, which was awesome, right? That's really cool. So then I arrived at Harvard. This is a departmental file server. This is sticking tape. I think this technology is a password or some kind of login. It was not awesome. It was really, really, really bad. So we thought, how can we fix this? And so we decided that we would deploy incentives. So we would incentivize our research faculty to be able to use compute. And so we incentivized them with a great big computer. This was a 4096 processor machine, 2008. I guess you guys were releasing version 1. We were busy standing up this machine. What's important is this is a screen grab from the first kind of submission, and this is our output from LSF. You can see here we were using platform OCS to bootstrap these things and kickstart them. The important part was that the top priority queue was called Nancy. She was our then Dean of Finance and Administration, and we thought it was real cool that the faculty would have to submit to Nancy, right? Because she paid for the computer, so we thought that was cool. So today, long story short, we're about 70-odd thousand CPUs, about 35 petabytes of disk. The important point I'll come back to is that we're growing at about 200 or so kilowatts every 6 months. That seems to sort of be the standard unit of issue. We run through about 2 million workloads every month, and so those are individual compute jobs. And there's only 25 people running around trying to do all of that. So we own everything from the network to the data center to the software to the orchestration. So we don't have huge staff. And this is how I always think of how we annotate our organization. So this is a data center over here, and this is research faculty. Imagine you take a prism, and you take white light, and you separate it out into the ultraviolet and the infrared. So in infrared here is operations, wires, data centers, racks. And over here is our research faculty. What we are trying to bridge with OpenNebula is this bridge here between the software infrastructure abstracting from the operations so that we can kind of get at it. So it's sort of ops, dev, DevOps, science. And so you can think of this in kind of a Maslow kind of hierarchy, self-actualization, esteem, belonging and love, safety, and physiological, and that maps really nicely to, you know, science and outcome. Faculty and tenure clearly are in esteem. Belongingness and love, we put in informatics because my wife runs the informatics group, so that's there. But then the basic underlying of all of that is that, you know, you have to have a Twitter account, right? So it doesn't matter what else you have, that this is the underlying hierarchy. So I want to mention how important green concepts are to us. And Kermit said it isn't easy being green, and it really isn't, but it helps when the university president says that you have an aggressive 30% reduction in your footprint, and she's in charge. So that actually helps a lot of both investment and focus on kind of compute and storage. So the real difficulty why it's not easy being green is that we're here in Boston, Cambridge, and our data center is out here in Western Mass, and that's about 100 miles or so. We have, you know, very sophisticated networks to be able to get from here to here, but we went out there because of this. So this is a large hydroelectric facility. So Holyoke was an old paper mill town, and so very little paper gets used these days, and so Holyoke had this large, I think 30-odd megawatt hydroelectric facility that was underutilized. So we were able to build a massive, great big data center. And we couldn't do it alone. We actually had to partner with MIT, UMass, Northeastern BU, and Harvard. So you imagine some of those phone calls we had trying to discuss what we were going to put in the data center. We didn't kill each other. It was pretty amazing. But we opened in February 2013, and our little research computing organization here at Harvard is responsible for about 45% of the current fill rate. So we got a great deal. The finance team love us. And it really was a lot of building. We built a physical building. And you can find out more about it at MGHPCC.org. This is one of the problems of running as a consortium. You come up with ridiculous names for things. So it's the Massachusetts Green High Performance Computing Center. Much email about that name. And it's the real deal. Here's me and the executive director. It's a huge, great big data center floor. And it is, you know, there's some latency here. So especially when you have to get in your Subaru or your Jeep and drive out there, it's a concerted effort. And everything's super scale, right? So there's a little me, and you have one of these at home. It separates the air bubbles out of your cooling and heating system. It's just, you need a really big one. And so we opened it, and then about 3 years later, we filled up our allocation. So this is the rise of the kind of compute. And so this is important. So this was June of last year. We extended our space in the data center. And this one's important to kind of give you a feel for how these things get done. So this is Pat Larkin. He works in the state. This gentleman's our VPR, our Vice Provost for Research. There's a little Englishman here. This is John Goodhue. He's the Executive Director of the center. And then this is Alex Morse. He's the Mayor of Holyoke. So it just shows how much impact you actually have in the local community. More importantly, the chap standing next to me is Russ Porter, who's the Dean of Finance and Administration. You can tell because he's got very short arms. He can't reach his wallet, right? So when he gets it, you get a hold of it, and you get him to pay for things, which is great. So science, right? So why do we do all of this stuff, right? So we want to understand how the flu works, and so we have machine learning for flu. We want to understand how basketball works, right? We want to understand how players work, and we do machine learning and all sorts of data analysis. We want to understand earthquakes and viscoelastic models, and so we do a whole bunch of that. And then there are some crazy people who want to simulate an entire virtual universe, so we do that as well. And so it's pretty impressive, the kind of research that goes on. This particular chap puts a telescope in the South Pole so that the Earth doesn't move and stares into the sky looking for cosmic background radiation. It's pretty impressive. This one was really impressive because this happened. So this is when scale comes and creeps up on you. This was 11 o'clock in the morning. This project was announced, and these guys and all of their friends, and this is what happened to our network. Bink. We didn't have the password for the DNS for the name of that web server. A postdoc had it, and he was at the conference. So one VM took all of this, because we couldn't put it behind our load balancer because the postdoc had the password for GoDaddy.com, right? So sometimes scale comes and bites you when you're not expecting it. The other thing about science is we're able to stitch together some amazing people at Harvard. So these are folks that work on neural plasticity, genomic imprinting, and connectomics. And we're able to kind of bring all of these folks together under an umbrella of informatics and research computing, to a point where we actually have a $28 million project to try and understand the wiring diagram of a brain. So only people at places like Harvard could even conceptualize the idea of doing this. And I'll come back to how we kind of tackle that. We're building new flow batteries. So these are, turns out, vitamin B12 compounds. So these quinones turn out to be really good for making flow batteries. And so flow batteries are not toxic, and they can store energy, and you can put them in places where you wouldn't put normal power. And you solve for this by doing a lot of quantum chemistry, massive scale, distributed all across the world. We write the same quantum chemistry software to be able to understand and develop new organic light-emitting diodes for televisions. So the blue LEDs are really quite difficult to make. And we can teach computers how to sniff, which is kind of interesting. So we do a whole bunch of that. But we need a load of disk to be able to do it. And so this chap is Jeff Lichtman. He's one of our professors of neurobiology, and he has an electron microscope. And it generates 3 terabytes of data every single hour. So this is the way that they're understanding the brain. They're taking these tiny, tiny little slices, and they're effectively taking 61 pictures in one go. And this machine drops out one of those pictures every couple of minutes. This is a 100 terabyte volume. So you take 10,000 by 4 by 4 by 30 nanometer slices, and you use that to be able to then stitch together the human brain. To put it in perspective, when I was at the Sanger Institute, that earlier picture, the entire Sanger Institute was 3 terabytes. It was all made out of 4 and 9 gigabyte hard drives, and it would fill rooms. So that one machine does a Sanger every hour. It's kind of interesting, right? So how do you keep up? We perform unnatural acts with computing. This is what we do. These are not warranted. No vendor in their right mind is very happy about doing this, but we do it notwithstanding. And we try and stuff as much possible compute into a small amount of space as practically possible, so that we can basically segment those images and rebuild the wiring diagram of a brain. And so by hand, this would have taken 1.25 centuries, and we can get it done in about 25 hours. We're trying to get that down to an hour. Can I get it down to 15 minutes? I'm going to keep going. So this thing about this storage problem, everyone can rack and stack disk. It's dead easy. Thank you. We've been putting petabytes together for a good length of time. We can now squeeze just short of 3 petabytes into a space this big. So that keeps Jeff, our neurobiologist, happy for a couple of weeks. So you feel really proud when you stand one of these things and think like 2.8 petabytes, and it's like 2 weeks. Just want to make a plug. Storage is not these things. They're great. I'm sure people love them at home. Dropbox is a lovely technology, but this does not scale. And if you want to find out how things don't scale, there's a little angelic bunny explaining to one of their research faculty about the no_backup directory. It's valuable listening, right? And so we never have enough space. It's a constant battle. But we and our partners who built the MGHPCC also realized that we didn't have enough space, and we were able to have a conversation with the National Science Foundation. This is a $4 million award that Wes, who's here, is our lead engineer on. And so this is going to do what we did for the data center, but for storage. So we're in year 1 of a 5-year project. And these participating institutes are going to be able to build a 50, 60 petabyte big shared object storage. So we're here to talk about clouds, right, and sort of hybrid clouds and compute. I'm going to argue that this is cloud, right? You're 100 miles away from your data center. You're going to need tools and techniques to be able to manage that compute. We can't constantly get in a car and drive up and down. I live about here, so I'm sort of midway. It's easy to commute this way, less so that way. So when I met this gentleman, we realized this is a cloud. And he said, I think I can help you. I've got this software, but more importantly, I've got this team, and I think we can help you get your compute out of here, over here, or basically wherever you want it to be. So we were really fortunate to be able to have Ignacio as a visiting scholar here at Harvard for the last year, embedded and working with the team and great technology. And he's continued to build this work at the RCC about challenges in federated cloud computing, and I'm going to argue and posit that federated clouds do and really do matter. To the point where the inevitability of public and private cloud infrastructure, there's a great article in the Next platform that's definitely worth reading about that whole wave-particle duality of both cloud and compute and storage. So just to wrap up in the last minute or so, to OpenNebula, like why OpenNebula, why am I here? This was how we used to do it. So Matt now works with Spotify. He was one of our DevOps people before they were called DevOps people, I guess. I don't know when that started happening, but it's happened. So this is around 2012, and this is an email to our list about balancing KVM hypervisors. So at that time, we had 137 VMs split over 8 hypervisors. And this is technology called a Perl script. And so the Perl script technology was how we would manage and schedule virtual machines. It kind of worked, but this will not do. This was not the way to be able to kind of do compute. And we were real fortunate about 2 or so years ago to hire Justin Riley, who's going to speak at much more detail than I have, who came to us, and we were trying to solve for this challenge of the Perl scripts and the kind of technical debt that he'll talk about, how we paid it down. And I found this is kind of cute. And so Justin Riley mentioned me in the room, RC OpenStack. There's a clue there, not to just, but it's out there, so I'll just leave it as it is. So that was the room, is what it was called at that time. And clearly I was idle because it was 3:13 p.m. I was obviously at a meeting or sleeping or something. But Justin says, "Hey, Cuff, NOS," and John sat right next to him. Just a quick note, I gave OpenNebula's VirtualBox Sandbox a test drive last night. Good stuff, hyphen, actually worked, exclamation mark. Right? So we knew we were onto something, and then we renamed the chat channel. And the rest, as they say, is history. We've just published some work together with Ignacio and Justin and John and Wes and myself that's in the IEEE Computer Society, a high availability cloud for research computing that Justin and the crew are going to dive deeply into. Thank you very much for your time. I know that was a lot to digest, but it sort of should give you a feel for why these public-private clouds and why the software that you're going to talk about today really matters. So thank you very, very much. Appreciate it.